So let's talk about few more tutorials. Now we talk about something like steady state and the transient part, but when we talk about the transient, we try to look at both density based and the pressure based, both class of solver. So first let's have an idea about the steady state class of the tutorials. Okay, so here we're going to work with the row simple form. Okay, so row simple form is the solver, and we have a couple of tutorial we have, so let's explore that. Okay, so first create the environment. Okay, so here is our readme file. So first clean the case, block mesh, and then we have idea about the mesh and all other parameters. So this tutorial straight away I adopted from the release version. Okay, so if you go to tutorial section, you will see the same class of tutorial available. Okay, so this is very coarse mesh, and we have a sharp angle, not sharp angle, but we have an angle in the duct. Okay, and we want to explore how the property is changing within this duct, and we want to simulate steady state class of calculation only. Okay, so let's have an idea. So here is the inlet patch, okay, and we have an outlet patch, okay, inlet and outlet. Okay, and then we have a different walls. Okay, then we have a porous wall. So in this zone we specifying explicitly some class of the porosity. Okay, so to generate the resistance within the domain, that is the idea. Okay, and then front and the back side both. Okay, so that is what we have a different name of the all the patches. So let's explore few more entry for this test case. So let's start with the thermophysical property. Okay, so we want to work with the transport as a Sutherland, and when we work with the Sutherland, these two coefficient is required. Okay, and we are working with sensible internal energy base. Okay, and perfect gas we are working. Okay, so that's why we have a Cp and Hf equal to this value. So now let's also look at turbulent properties. So we're going to run with the runs and k epsilon base model we're going to run for this particular tutorial. Okay, fv option, that is new file available. Okay, that will allow you to set the porosity. Okay, so it is the explicit porosity, so it will trigger the resistance to the flows. Okay, so that is what we set here. Okay, so this is the porous zone. Okay, anyway, we are not interested in this porous zone or anything, but we are interested how to simulate the particular steady state version of compressible flows. Okay, so let's have an idea about all these files. So in the start with velocity. Okay, so we have a inflow flow rate, inlet velocity. So we specify the flow rate with which the velocity is entering inside the domain. Okay, all the fixed wall except the inlet outlet. Okay, in the porous zone we are specifying the slip wall conditions. Okay, within that zone. Then temperature 293, and everywhere on the wall it is gradient, and inlet outlet we saying the compute from the internal field. Pressure 101, almost atmospheric pressure we specify there. Okay, and then we have a outflow condition. Newt wall function we are specifying. Okay, KQR wall function we are specifying at the inlet turbulent intensity, and we specify the intensity. Based on that, it try to calculate the K and epsilon value. Okay, and outlet, inlet outlet epsilon same way. Okay, we have this particular mixing length, and from that it try to calculate the epsilon. Sorry, from K it with the intensity try to calculate the turbulent kinetic energy, and with the help of this mixing length and dissipation rate inlet, if we specify the mixing length, it gives us the value for the epsilon, and alpha t is the thermal diffusivity. Okay, so that is what we have, all these boundary conditions. And then in the system folder we have this couple of options here. So we work with the row simple form, and we're going to run for something like 1000 iterations. Okay, scheme wise we are working with the upwinding class of the schemes, okay, to stabilize the flow. But later on, if you want, then you go with the center linear scheme. Okay, that is also one of the way. Okay, then simple algorithm. Okay, so let's start with something like a more restrictive row value. Okay, something like 0 to 0.2 only. Okay, mean and max. So let's have an idea what is what happen if we restrict these values. Okay, later on we leverage this value, and the residual fall what we are expecting is 10 to the power minus 4 or minus 3, and relaxation parameter we set. Now let's run this case. Okay, so look what is happening. We restricted the row value. Okay, so it try to restrict within that range only. What we gave here is this row range. Okay, so it don't go very far away from this range. Okay, so that is what exactly happening. We restricted to row equal to this, but we don't know, we cannot restrict the row formations. Okay, so this is going to be the wrong calculation. Okay, so what one has to do, one has to leverage this range. Okay, so normally if you see that your min max value is approaching whatever you set in the simple algorithm or in the simple here, then you supposed to change this value. Okay, so let's say let it be 0.1, but higher side let go something like 1.5 or so. Okay, so what happened, it will give the leverage to the row so that it will go within this limit. Okay, so sometime it happened that it going to shoot out. At that time it try to restrict this particular value. Okay, but normally what I suggest, if this value is approaching mean and max, then try to say relax these values. Okay, for the better result. That is what one supposed to do. Let's say 1.5. Okay, now let me run the case again. Okay, now if we see the value, okay, so value is going in between this. So look, we restricted the row formations. Okay, so when we restrict the row, immediately it has a effect on all other field as well. Okay, so we cannot restrict the formation of rows. Okay, and what we supposed to observe here, okay, let's say in some of the cases you find that it is very difficult to convert the case. Okay, this is not happening for this particular case. It's converging very nicely. If you see that this value is not converging. Okay, so what you're supposed to do, if this value is not converging, then if the first look at this relaxation parameter. Okay, and try to relax these values. Okay, if the pressure is not converging, then we have a nice way to treat the pressure is by increasing the more number of the non-orthogonal corrections. Okay, when we increase the non-orthogonal correction, immediately we will see pressure is going to converge much better. Right? If you look at here, it till is taking something like 2 iteration or so. Okay, but if you want, we can increase that. Okay, so let me run it again. Okay, so what I'm doing, I'm right now changing this value something like 5. Okay, and let's rerun this case again. Okay, so when you do that, okay, it's going to converge very nicely. Okay, so pressure going to converge. Okay, so pressure slowly going to converge. Okay, so sometime if you think that pressure is not converging, okay, it's not going 10 to the per iteration, supposed to reach 10 to the power minus 5 or so. If not happening, okay, then it is better to increase this in between corrections. Okay, and parallelly also, if you see that velocity is not converging, then you have to change the relaxation parameter for velocity. Okay, so either of these things is going to help you for the convergence. So when we work with this compressible flow class of the calculation, then sometimes it's very difficult to convert the solutions. Okay, at that point of time, maybe it will be helpful to you. Okay, so let me see the result, how exactly it look like. Okay, so before that, let's calculate the Mach number. Okay, it's still running. Okay, no problem. So look, velocity almost except the z component, everything reached very nicely. Okay, so because of this, it's taking little bit time. Okay, when it also converge, we're going to get a converge simulation very quickly. Okay, right. So fine, it's after 756 iteration, it's over. Okay, let me recompute the Mach number. Okay, and P total as well. Okay, so we have a P total and the Mach number both. Okay, Terraform. Let's see how exactly it look like. So let's go to the last entry, look at all the values. Okay, and on this, let's construct the one Z plane and have an idea. So 2D to 3D. Okay, fine, and let's look at the Mach number. Okay, so up to here, free flow. In this zone, we have a porosity, so we have a restriction, and also we apply the inviscid wall or maybe the slip wall, so you will not see the boundary layer creation within this zone. Okay, U value also you will see in the similar line. Okay, so from here flow is entering. Here we have a restrictions because we specify the porosity, try to restrict the flow. Okay, and because of that restriction, we will see the little bit change in this particular place. Okay, so it's not always always the case that when we work with the compressible flow, we always have to think about the shock and everything. In this class of the case, even the flow is compressible. Okay, but the shock formation or nothing going to happen. Why? Because if you look at the Mach number, it's hardly, okay, so very low Mach number flows. Okay, so but our fluid is compressible, that's why we are working with the compressible class of the solver. Okay, so this is what we see from here. Let me see the pressure. Okay, so this is the pressure what we get out of it. Okay, so this is very simple class of the calculations. Okay, where we have a angle and we specify the incoming flow in terms of velocity, and we have a outflow. Okay, so this is very simple test case to simulate with the help of the steady state, and but we work with the turbulence model. Okay, so that is difference here. Okay, now let's look at one more test case. Okay, very quickly. So we have a idea about some setting related to the simple form class of the calculations. Okay, so first let me clean the case. Okay, then we start the calculation. This is another case where we have a U band, but the cross section is the square cross sections. So idea is that we try to look at the flow profile inside of it. Okay, so block mesh, Terraform, right. Okay, so here is the inlet and here is the outlet. So let me give you the idea. This is inlet, this is the outlet, and all are walls. Okay, so inlet, outlet, and the wall. Okay, and this is very coarse mesh we have. Okay, so we try to simulate the flow field in this U band class of the geometry. Okay, so let's explore both the properties what we have here. So we work with the K epsilon model, and thermophysical, again we working with the Sutherland and the similar class of the setting. Okay, now let's go to the boundary condition area. Okay, so we require the boundary condition for all the fields. So at the inlet we saying flow rate inlet we specified. Okay, and at the outlet same inlet outlet. For temperature all we have a something like 1 1000 Kelvin temperature we specifying, okay, and the pressure we have 1100, so 110K pressure we specifying, okay. At the inlet also 0 gradient, okay, and at outlet this is just fixed value we specified, okay. So this is the pressure conditions, nu T, okay, NT Q wall function, KQR wall function for K, epsilon wall function for epsilon, and compressible alpha T wall functions for the thermal diffusivity, okay. So this is our setting, okay, and now let's run this case. So you try to run it, okay. I already run that case, and let's quickly look at the result, how exactly look like the result, okay. So here we don't have any porosity or anything, okay. It's very simple flow inside the duct, okay, and but the flow of a compressible fluid, something like that way, okay. So let's quickly cut the cross sections, okay. On this cross sections, let's have an idea about, let's say, U, okay. So velocity is something like 557 or so in this zone, so that is the area where we have a high velocity, okay, and very nice boundary layer is developed on that, okay. So this is very simple, again the test setup where you have a compressible flow through a duct. So normally when we talk about the HVAC design or so at that point of time all these settings people normally use for steady state calculation, where they are not interested in transient calculations, okay. They are interested in simple class of calculations for HVAC duct design and all that concept, okay. So this is again a very simple example, so I suggest please go through it, okay, and try to simulate both the examples and have an idea about the steady state solver, like a row simple form, okay. Now let's move towards the unsteady part of the solver. So for that we're going to use the row pimple form, okay, and for the row pimple form we have very nice setting of the test case, okay. So let's explore this. So before that let's again have an idea about both the solver, whatever right now we are discussing. So one is the row simple form, just now we look at, so it is a steady state simple solver, okay, for laminar or turbulent trans flow for a compressible fluid. So that is about the steady state calculations. And if we talk about the pimple, okay, again we have a same transient solver for laminar turbulent flow, okay, for a compressible fluid for HVAC or similar applications, okay. So here it is transient, this is like a steady state type of calculations, okay. So let's quickly look at this particular test case, okay. So for that let's look at the readme file, okay. Here we have to do certain few more things for test setup. So before that let's first clean the case and then generate the mesh and have an idea about first entire setting, okay. So this particular test case we're going to run for by two solver. One is the pressure based solver, that is row pimple form. Another is the row center form, that is the density based solver, okay. So we try to run and try to compare both the result, okay, with the help of the different solver. But the physics, how better way we able to capture, let's have that exposure with the help of this very simple tutorial, okay. So let's first generate the mesh, okay. Now let's look at the mesh and have a understanding about our test case. So this is something like a very large tank filled with the liquid or any of the fluid, okay, and with this one convergent divergent nozzle is attached, okay. So when the fluid is released, okay, how the shock is triggered within this area, okay. So if you do the simple compressible flow calculations, okay, for that if you require the location of the, let's say, Mach number, and on particular locations you can figure it out, and for shock location at particular nozzle you can figure it out what's supposed to be the pressure range here. All these thing calculations you can do it, but what we right now doing is very simplified class of the calculations. So for that let's first have idea about both these files. Okay, so we work with the laminar flow. Okay, that means no turbulence modeling we're going to use, so we say it is a DNS class of calculations. Okay, and we have a H Thermo. Okay, and so that's why we have a CP. We work with the inviscid flow because mu equal to 0, so we are not taking into account the viscosity effect here. Okay, but later on if you want, then you can switch on the viscosity and have an idea. But when you switch on the viscosity, immediately your delta T requirement goes very low. Okay, so you have to be careful with the divergence if you observe. Okay, so here we are working with the inviscid class of the flows. Okay, and it is perfect gas that we're going to use. Okay, and sensible internal energy is the setting what we adapted. Now look at these all files. Okay, MA is the Mach number file, is the dummy file. Okay, nothing else there. So what we gave just uniform some velocity to initialize the flow field. Okay, otherwise at the inlet outlet we say gradient equal to 0. Bottom is the symmetry plane and top is the slip. Nozzle is also slip, so please understand all this entry. So we have a inlet and outlet. Okay, so this is inlet and this is inlet and outlet. Okay, so inlet, outlet, and we have symmetry plane. So below one is the symmetry plane. So bottom, okay, on the symmetry plane is nothing but the bottom. Okay, so that is what we have here. Okay, then top is this is the top patch. Okay, then we have a nozzle. Okay, so this is nozzle area. Okay, so all this is we specified as a slip conditions. Okay, because we are working with inviscid flows, so no need to specify any fixed value, because anyway we're not going to generate the no slip conditions. Okay, so that's why we specify the slip condition over there. Okay, and front and back is the empty. Okay, so this is the conditions on the all the walls except the bottom wall. Okay, so this top and the nozzle wall we say it is inviscid wall. This we say bottom wall is a symmetry, inlet and outlet. Okay, so that is what we specify the condition. Temperature we say 298 initializations. Okay, because now pressure energy is going to converted in terms of the kinetic energy and the temperature is triggered. That is what we're going to do. So we gave the something like 3 bar as a pressure. Okay, so inlet we say total pressure we specified. Okay, and the outlet we gave the certain low value of the pressure. Okay, so normally depending on this both the pressure we can trigger the shock. Okay, so we have to do some back calculations from the simple gas dynamic calculations, and one can figure it out what's supposed to be this pressure ratio that give you the shock. And it all not only give you the shock, but it also give you the, by calculation you can quantify what is the Mach number near the shock and what is the location of the shock. All these things one can quantify based on the compressible flow fundamental calculations. Okay, so but based on that calculation, let's say we figure it out that at the inlet we require the 3 bar and the outlet we require the lower pressure. Okay, so and that going to generate the shock in the nozzle area. So that is why we are specifying these particular conditions. Okay, now let's look at the few entry from this side. Okay, so let's talk about this row cent we are working with the row pimple form only. Okay, but I didn't change the solver name, so let me change here pimple form. Okay, because I adapted this tutorial from the row center and then again generated for row pimple form. Okay, to give you the comparison between two solvers. Okay, now delta T going to be very low because we going to work for very high speed flows. Okay, and the time requirement is only 1 second, so within 1 second we want to simulate, and the current number we fix equal to very low value 0.1. Okay, and we are fixing certain probes. Okay, so what we are going to do, we try to fix the probe in this particular zone where the shock is going to trigger near to the shock area. Okay, so that is this is the location. You can keep more probe to exactly watch the shock formations. Okay, but I kept 2 probe in this zone, okay, away from the central axis. So on that we try to record the these three quantities, it gives us the idea about the progress of our simulation. Okay, so whenever we try to work with the transient solver, it's always good to have this all certain field output. Okay, it gives us the idea how our simulation is progressing. Then scheme wise, we are working Eulerian scheme. You go with the backward scheme or Crank-Nicolson's. Okay, then this gradient scheme, we have a linear but limited linear, we are using cell limited. Okay, and the divergence scheme, we are working with the linear upwinding for vectors. Okay, so I suggest later on you try to work with the even everywhere the linear scheme in compared to the this upwinding class of the schemes. Okay, so it give you the better capturing of the shocks definitely. Okay, so this is what we have. And in the in the solver side, we are using with this PCG. Okay, and our other solver is BiCG stab. Okay, and momentum predictor is yes, and outer corrector 1, and inner corrector 2, non-orthogonal correction equal to 1, and this is the rho min max value. So when the simulation progress, if you find out that this value is shooting up, then you have to tune this parameter. Okay, if you're not tuning this, then sometime you get the divergence. Okay, so when you get the divergence compressible flow, always first check this value. Okay, either it is not shooting up. If shooting up immediately, you can leverage this value, because if you have proper idea what's supposed to be density, then give a proper that range. If you don't have idea, then this is the way to go. Okay, so let's start the calculations. Okay, for this based on the rho pimple form. Then we look at the rho center form again. Okay, but meanwhile let's start the calculation. So maybe it will take maybe half a day or so. Okay, so I already simulated, but let me show you when you start the calculations. Okay, I'm not going to simulate it every again. Okay, but just give you the idea. So we working with the pimple loop. Okay, so one pimple loop. Okay, and then we have a predictor. Okay, energy equation. Then we have a corrector step. Okay, we specify the 2 time inner corrector and 1 orthogonal correction. So that's why you are seeing this all different entries here. Okay, so this is what you can see the output. Okay, but I already run the case. Okay, so we have to do the post processing, but I suggest you run it, because I'm not going to give you the all the datas on the our Google Drive. Okay, so I give you the setup only, and you have to run the case, both the case. So before we go for post processing, let's also look at the setting for rho pimple form. Then at a time we try to do the post processing, because same test case we're going to run for with the help of the rho central form, and I already run the case. Okay, so entire data is with us. Okay, for post processing, but let me give you the quick idea about this as well. Okay, so laminar again transport property. Okay, so we have a H constant is the transport property, so make sure your transport property doesn't change. Okay, so fine. So we have a same transport property. Okay, turbulence model is off. Then talk about the boundary conditions. So go in this area. Okay, so we are working with laminar flow. Okay, so we have this conditions, same conditions we have. Okay, here symmetry, slip, temperature we are specifying same way, pressure also we are specifying same way, no change in the boundary condition, same boundary condition we have. Okay, only you can observe the change in the schemes area. Okay, control dict file. Okay, so same way we work with the point not 1 is the 0.1 is the current number. We also fix the same location the probe to compare the both the solver. Okay, and now we are working the rho central form. So let first go to the rho central form area. Okay, so it gives you a certain idea. So rho central form. Okay, and let read the its guideline. So density wise compressible flow solver based on the central finding scheme. Okay, so it is a specific scheme. Based on that, this entire solver is written, and it is dedicated solver for compressible flow class of the calculations. Okay, so it definitely going to give you the better result, not only better result but faster convergence as compared to the pressure based solver. Okay, so that is what you will find the difference. Okay, flux, we have different thing, but definitely when we work with the compressible density based solver, this interpolation also matter a lot. Okay, so so normally for all row center tutorial you will see the one this Vanley as a interpolator. Okay, so in case of that we are using 1 L-Bada, okay, or 1 L-Bada V as a interpolator. It give you the much better result, and it try to also suppress the or remove the oscillation from the flow field. Okay, so that is why we choose these schemes. Okay, but if you look at our set default tutorial, you will see the Vanley is the normal scheme people choosing. Okay, then okay, here I didn't run with the same solver, but I suggest you try to run with the similar solver. Okay, like BiCG tab here. Okay, I forgot to change basically. Okay, so this is what the solver setting we have. Okay, now I already run both the case. Okay, so idea is that we want to compare the results. So first we try to do the post processing by normal way. Okay, so normal way, that means we go to the first the pimple area, sorry, yeah, pimple row pimple form. Okay, and here is the our entire data. So let's look at the this result. Okay, and then we try to open over this row central form results. Okay, so here is the, okay, before that let me check Mach number is calculated or not. Okay, not. So let me first construct the Mach number here. Okay, so Mach number is almost near about 1.84 or something we are getting. Okay, so let's generate the Mach number and the total pressure. Okay, so the two things we are generating. Okay, we have to generate for both the side. That means we also supposed to generate for row center form as well. So let me go to that area. Okay, so this is row center form area, and here I have a same backup file. So 0.8987. Okay, so little bit higher side we are getting the this Mach number, slightly difference you will see. Okay, so total pressure, and then we start our post processing of this particular test case. Okay, so I run at a time both this case. So it took something like for on my laptop more than 14 hours or so. Okay, so in fact I run at a time 3 different cases. Okay, so that's why, but I don't know, based on your configuration it will take time of your PC. Okay, so let's go to this area, and we want this folder. Okay, now let's look at the test case first. Okay, how the shock is formed and what exactly happened. Okay, so this is the test case, and let open this. Okay, okay, fine, applying. Okay, now because we construct this symmetry, so sometimes it is good to construct the entire domain while we are doing the post processing. So for that, from the this alphabetic order, you try to activate the reflect. Okay, this one. So start the reflect, and reflection is with respect to y-axis. Okay, perpendicular to your symmetry plane. If you do that, we get a entire of this domain. Okay, and on this let's have an idea first with the our velocity field. Okay, so this is the how it's look like. Okay, change the legend, okay, as a horizontal. Sorry, not allowing me to do that. Fine. Anyway, okay, so this is how it's look like here. Okay, and then let's start the calculation. For that also, let's activate the filter of something like annotate, okay, time filter. Okay, apply it. So I'm keeping the time here. So here is the time. Okay, so let's start the calculations. Okay, so look, it oscillating here and there, and slowly it going to get a final steady state location of this particular shock. Okay, so that is what going to happen, but it going to take a longer time. So I didn't run till it stabilize it. Okay, so if you want, you can run till it stabilize, and you will get a so sharp location of this particular shock. Okay, so that is what you can observe from here. So it's at the beginning it's oscillating very large, but when the time progress, the oscillation is damp out, and finally you will get a steady state location for the shock. Okay, so let me also open along with that our central form data as well. Okay, so here let's open the other test case as well for comparison point of view. Okay, so row central form, and we have a entire data. Okay, so let's open here, and for that also let's construct the reflect. Okay, wait a minute, filter, recent, reflect. Okay, along the y direction, apply. So we have this as well. Okay, now what we do, we try to partition this in this way. So here we have this rotation. Okay, and this value we have here. Okay, fine. Same way, let's generate the same thing here. Okay, so okay, fine. So here also let's see the u value. Okay, so almost it looks similar. Okay, so let's start the calculation from the beginning. So slowly look how both the simulation progress, you will see the result. Okay, from here. Okay. This is the simple contour plot, but later on we try to look at the exact line comparison. It gives us the better idea exactly if we see. So slowly it try to damp out. Okay, and this is all the expansion waves is triggered. Okay, within this particular domain, and it is exactly a steady state class of the calculations, but we are working with the transient algorithm. Okay, so it going to take time, but if you want, you can work with the this row simple form and try to simulate this test case and have an idea either you are getting the proper location or not. Okay, so I suggest you do that exercise as well. Okay, so this is how slowly the oscillation for both the solvers is damp out, but both are oscillating, and look at the sharpness. Here you will see very sharp capturing of the shock as compared to this, and because we are using some type of diffusive scheme, so you change the scheme for the row pimple form, and you also may get very nice sharp things. Okay, sharp shock. So let's have an idea about the shock, how along the shock how the property is changing. For that, let's create a something like new filter, so flow a line and we want y line, okay, but here we want, okay, so line y line, okay, and let's say apply, okay, so but we try to look at the line here itself, okay, so I'm switching off this reflector, okay, and I'm okay, so what I do, let me switch off first this, delete, okay, let me delete this as well, so we have these two things, and now let me create again the new filter line here, and we want X line, okay, apply, so this is for the first one, okay, so on the first one we get this same way, let's choose this filter recent one line X line, okay, apply, so this is the line for second one, but let's have idea about all the properties of line, okay, so let's switch off everything, let's have a Mach number here, okay, same way for second, switch off everything, okay, but and okay, let me switch on the Mach number and all these quantities, so we have here, okay, now let's go back, switch off everything, and let's have a Mach number. So look, this is how the Mach number look like. This is for center difference, row center form, okay, and this is for the pimple form. So look, when we talk about the, this is for this is for row pimple form, okay, and if we switch on and switch off, this is for row center form. So with the row center form we get a very sharp gradient here, okay, so that is the idea where exactly the shock happen. You can tune this axis, so exactly more or like similar class of the range if you want, then you go ahead and let's tune something like 0.25 or so, okay, so till it is far away, let's say 0.35, so I am checking where exactly this is happening, 0.38, it gives us the idea, so more or like here, okay, now just run the case, okay, so look slowly how it is built up, but let me also activate both the things, okay, so let's start the oscillations, okay, so slowly shock is built up, okay, so with the help of different solver you can compare how better way you be able to capture the shock, okay, so that is the idea, okay, so this is the Mach number calculations, okay, how the Mach number is vary, so maximum is something like 1.8, above 1.8, okay, so that is what we are observing here, okay, but the row center form give us the better capturing of the shock, and it is correct also because it is based on the density base. Not only that, in case of the pimple we use the diffusive scheme, so that is also a little bit change. So if you want, then you can change the schemes and have an idea what exactly happened, okay, so let me stop this and go to the last one, okay, so location wise it's almost same, okay, at that particular instant, okay, but if you see the capturing is little bit different for both the case. Now let's have an idea about, let's say, temperature at that locations, okay, switch on temperature, so look, temperature capturing, okay, here also let me change annotation to temperature, so we have an idea, so above shock we have a low temperature, immediately after the shock we get a very large temperature jump, okay, so that is what we observe here. So in this zone the entire energy is converted thermal to the kinetic energy, that is what we see from this side, okay, so this is what we are seeing. Then look at the velocity, okay, so velocity and the Mach number almost look similar, and then the pressure, okay, so this is the pressure, how it is changing. So this is how one can see very quickly the formation of shock with the help of these two solver, okay. So what I suggest that please run with the one thing you can do. First try to run with the row simple form. Okay, and are you getting the location appropriately? So just change the solver setting and go with the row simple form and run for the steady state calculations. Then you can tune the schemes as well for row simple and the row center form, row pimple form, and try to compare the data with the row center form. So your base benchmarking data is the row center form, and with the row center form we try to compare the data for row simple form and row pimple form. Okay, so that is one can do very quickly. Okay, so this is what we have for this. Along with that, we store a couple of probes. Okay, so for that we have a certain things to look at. Okay, so let's go back to our previous place, and here we generated the probes. Okay, and here is all the probes script file. Okay, so right now I'm editing for my purpose. Okay, because this I gave the rename this particular folder as a different name. Okay, but when you work with the different folders, okay, so row center form, and inside row center form I gave this as a new name to that folder. That's why I'm editing that name inside the all the script file. Okay, so this name is supposed to be v. Okay, save for this file, okay, because we want to compare the probe between both the runs. Okay, and have an idea when the simulation progress what exactly happened at that particular probe locations, how the amplitude of all important quantities are changing at that particular location. So that is what we want to compare, and for that we are doing this or using this script file. Okay, so this thing we change. Okay, along with that, if you go to the readme file, okay, so I gave you certain commands to clean the U signal. Why you have to clean the U signal? Because if you go to post processing area probe 0 folder, okay, so if you open the U file, so let me go to that location and open the U file in the VI editor. Okay, don't open in Genie, and then it's going to take a longer time because it is a very big file. So look, here we have all this bracket, because U is a vector, so to store the vector we have a bracket for location probe 1 0 and a 1 probe and second probe. Okay, so we have to clean this bracket. For that I gave you this 2 command. So what we going to do, we try to clean both the bracket, okay, with the help of this command. Okay, and this is how one can clean the bracket. So we are at a row central form, so let me go to the other place where we talk about row pimple form. Okay, backup post processing probe 0. Okay, and here again I'm going to run this both the command to clean the U file. In the pressure and temperature it is a scalar, so we don't have that particular brackets. So to clean this bracket, use these 2 lines and you able to clean the bracket from the files. Okay, but now we have to work with the U final. So that's why if you look at here in the probe area, okay, so for U probe I work for the U probe I work with the U final, okay, in place of U. So this give me the exact comparison. So now let's go back to the area where our probe script file is located. Okay, so script file is, let me go back. Okay, so I have to copy the script file in this area. Okay, so that is available here, where I kept, wait a minute, row pimple area. Yes, so this is all the script file I am copying from here, okay, and keeping in this area. Okay, it already there, so no worry. So let me go to that side. Okay, so it is here. Now you use the GNU plot. Okay, and let's say we want to look at the pressure variation at the probe 1. Okay, so you can quickly see the pressure variation at prob 1, but here we are combining two cases. One is for red one is for row pimple form, and the green one is for row central form. So look, row pimple form immediately die out the variation as compared to the row central form. Okay, that is based on the density based algorithm, and red one is based on the pressure algorithm, and slowly both going to die out. Okay, so look, I almost started the simulation both at a almost same time. In fact, this green one, that is row center form, I started more than half an hour after the row pimple form, but it progress wise it goes very quickly. Okay, so when I stop both at a time. So up to that only 0.5 second, 4-5 second, the row pimple form is over, but the row center form is little bit ahead of it. So convergence wise also row center form is much faster and as compared to row pimple form. Okay, even though right now I use the diffusive class of the scheme. So when you go with the let's say center difference scheme, okay, maybe you will get a stability after a longer run as well. Okay, for this is so about the pressure. Okay, then we have a pressure at both the probes. So pressure at probe 1 and probe 2. So have an idea about the pressure at both the locations, how the pressure distribution look like. Okay, so sometime it is very nice way to compare the data, okay, for both the probes, okay, at a time. So this is about the pressure. Now let's talk about the first temperature. Okay, so this is the temperature variations. Okay, so how the temperature is varied, okay, on both the with the help of both the solver. So green one is the row center and the red one is the row pimple. Okay, and there is a certain variation definitely. Okay, so magnitude wise also there is a slight variations, and it damping wise also it's different. Okay, so because both the solver is definitely a different, so you will observe the certain differences here. Okay, so this is about the probe location 2. Okay, how exactly different variation we see. Okay, now let's have an idea about the velocity at probe 1. So I gave the small u, so we are looking at the u component of velocity only. Okay, that particular locations at a probe 1. So this is the u component of velocity, okay, at a probe 1. So this is what we see. Maybe it's stop in between of storing the data for probe for, let me see, did I run the in fact I run, so maybe something went wrong in my probe storage. Okay, that's why you didn't see the u velocity after the 0.25. okay, so something went wrong in the probe while it is generating. Okay, this is for probe 2 locations. Okay, so here also we will see the comparison. So what I suggest, you also run this case, but you run for different settings, like work with the row pimple form, and the one is whatever I gave it diffusive setting, then run with the center difference and activate the non-diffusive class of the settings. So try to look at that. Okay, and then also run with the simple form and compare the shock locations as well as property after and before the shock, and then have idea how better way one can capture the shock with the help of the steady state solver as well. Okay, so this is few things you can explore with this tutorial. Now I have a last tutorial for row center form. Okay, that is about the supersonic another nozzle. Okay, so for that let's quickly look at the setup. Okay, I already run the case, so we have to look at the post processing out of it only. Okay, so but few settings let first explore. Okay, so I will first introduce our test case. Okay, so here first let's clean the case. Okay, we going to work with the available mesh file, so you use this mesh file, okay, that I already gave. Now Terraform and have idea about the this particular test case. So this is axisymmetric in nature. Okay, sorry, something is failing. Yeah. 0 folder I plus row p total. Let me delete few of these entries. Okay, so sometime it is creating the problem. Okay, fine. Okay, what is the difference is problem is this wage. Okay, so okay, let me first rename it. Okay, then I will give you the idea why it is failing. So this modification you also have to do. Okay, so if you do the rename to the 0 folder, it allow you to see the everything. Okay, so look, this is the very simple test case. Here it is, we want to solve in the axisymmetric in nature. Okay, so what we going to do, we say that we try to construct this type of the triangular one wedge shape. Okay, and on this side and on this side we specify the wedge boundary conditions. Okay, so what we have an inlet. Okay, apply. So this is the inlet conditions we have outlet. Okay, so inlet and outlet, and on that we have a back and front. Okay, so back and front is we have to specify as a wedge conditions. Okay, and on the surface it is our normal surface. So this, when we import the mesh, immediately we have to modify that inside the block area. So what exactly you have to do, if you look at the 0 here, we say type as a wedge. Okay, so but if you look at in the boundary and the polymesh boundary area, sorry, let me open Genie, you will see for front and back it is a patch. Okay, so there it is failing. So we have to rename it as a this way. Okay, and then if you now rename the 0 folder again, okay, it will not going to fail to the normal way. Okay, so it's going to work with this. So I hope you understand. So on this we specify, so we are simulating very small sector of the entire circular cross sections. Okay, so for that we have a very nice condition in the OpenFOAM, that is wedge conditions. Okay, so that is what we specified here. Now let's have an idea of different settings. So we have a this transfer property not required. So we work with the laminar flow, thermophysical. We again working with the Sutherland and the Thermo. We have a Januf type of the thermodynamic setting we going to use. For that we have a high and low CP coefficient required, that we specifying here. Okay, and we have a Sutherland. So for that few more setting we have. Okay, so this is few entries we are specifying here. Okay, so then let's have an idea about first all the boundary conditions. Okay, so in boundary area we have a UP. Anyway, this is all dummy entry, so not required. We have to specify the value for this 3 on file only. Okay, so we are initializing with this. Okay, our driving force is something like a pressure. So at the inlet we specify the total pressure to 1/6, and the outlet, okay, it is a wave transmittive value. Okay, that is our proven boundary conditions, so it gives us the better outflow conditions. Okay, and then temperature we specified. Okay, at the inlet total temperature 388.115 degree. Okay, and the outlet again we have a transmittive type of the conditions. Okay, and for the pressure at the outlet 0 gradient. Okay, so this is our normal setting. Now let's go to the this 3 folder. Okay, so we going to work with very low delta T, and we want to simulate 4 10 to the power minus 3 only. Okay, it is a supersonic flows. Okay, so we need that's why we have to start with very low delta T. Okay, and the Courant number we fix equal to this. If you find the divergence, then you can tune it and go to the lower value. FV scheme, so we are working with this class of the schemes. Okay, right now we are working with couple of diffusive class of the schemes. Okay, but later on you can tune it to the required schemes. Okay, look, right now it is a Windley scheme, but if you want with the previous one, you can change it and go with that scheme as well. Okay, solution wise we are working with the smooth solvers, but you can go with the BiCG and change these solvers settings. Okay, non-orthogonal corrections we specified. Okay, so this is anyway, nothing is going to useful out of it except this few settings. Okay, so this is all are the dummy settings, because this setting is from the row simple class of the calculations. Okay, so it till over there only. Okay, fine. So let's start the calculation. So let me quickly start the calculation here and check it's running properly or not. It also going to take a very long time. Okay, so it also going to simulate maybe 8 to 10 hours. Okay, so but I already simulated this test case, so have a idea what exactly happened after your simulation over. So this is the backup file we have. Okay, again it is a half side, or we can generate the another half by using the reflect. So filter, use the reflect in the y directions. Okay, and construct the another half. Okay, so this is what we have here. So let's first fix this value right this way and have an idea about. Okay, before we go for that, let construct the Mach number. So Mach number slowly increase and goes something like 2.34, almost going towards 3. Okay, it's further increasing and going to 3.89, so approximately something like 4. Then it also again to drop out. Okay, after the okay, then we have a P total. Okay, so entry value missing. Which entry value? We say no 0, so it will exclude the 0 entry. Okay, so because on the 0 folder certain value is not available. Okay, like row, so that's why it's failing. Okay, so you can say no to 0, so it will not calculate on the 0th folder. Fine. So now we are set for post-processing this particular test case. Apply. First construct the reflector of it. Okay, in the y directions. So we have this. Now let's first have an idea about. Okay, let me go to the last one. We require this. Okay, let's say this as well. Okay. Okay, if I say P total. When P total you will not get on the 0 folder, it will may fail. Okay, so I'm removing at present. Later on we will activate. So let's have idea about the Mach number first. Reflector Mach number. Okay, let's go back. Okay, this is how it going to work. Okay, so maximum is going to be 3.89. Okay, so let's start the calculation. Slowly it's going to build up. Okay, so look, from this area the shock is triggered. Okay, and shock is moving across the diffuser sections. Okay, and then when it reached the diffuser section, after that it stabilizes over there and then try to construct the expansion wave class of the scenario out of it. Okay, so that is how you can see very quickly what's going to happen over that area. Okay, now let's have an idea about a few more quantities. Okay, so it's almost stabilized there. Okay, so let me stop it, and if you want, then let's look at in this area only, slightly oscillating. Okay, it's, you can see slight oscillation here, okay, but it's almost done. Okay, so this is how you can see here this value. Now let's look at the property after and before the shock. For that, let's generate the one file out of it. Okay, so let's line, okay, we have a X line, okay, and let's apply it. Okay, so this is how exactly it's look like, entire scenario. Okay, so we have a Z here, this value we are fixing over here. Okay, this is Mach number we have. Okay, so this is the how it's look like. So let's start again. So slowly Mach number is building. Sorry, let me first check, switch off all the entries that is not required and only activate the Mach number. Okay, let's rerun again. Fine. So slowly Mach number build up. Okay, shock triggered. Now shock is moving in the stringwise directions. Okay, so then yeah, so finally we get a this profile of a Mach number distribution. Okay, then let's see the temperature variation at present scenario, reflector temperature. So this is how the temperature is varying. Then let's look at the pressure. This is how the pressure is varying over here. Okay, and this is the velocity magnitude. Okay, so u magnitude. Okay, so this is how it's look like. So let me rerun again for velocity magnitude. So slowly it's build up. Okay, and finally it try to achieve the our desired Mach number, and for that the velocity is almost 850. Okay, so this is how the simulation it's look like. Okay, so one can work on this and finalize the calculations very quickly. Okay, so I suggest you try to run this test case. Okay, again for pimple form, as well as try to check with the steady state class of the calculation, because later on you will going to get a stabilized shock. Okay, a shock is not going to move after the shock. In between you have a transition phase, but at the later stage you will not get any transitions in the shock locations. Okay, so this case also you can run with the help of the simple row simple form as well row pimple form, and have an idea how better way we can capture the shock. Okay, so here I will show you a couple of the tutorials for compressible class of the flows. Okay, so it is not a very exhaustive class of the tutorials. Okay, but just give you the brief idea how you can set up the certain boundary conditions. Okay, what different parameter you have to take into account if the convergence is not happening. Okay, so this is the few things may be helpful to you.